Welcome to section 5.3. Everything's kind of building. Just like in intermediate algebra, when we looked at composite functions and inverse functions, they're immediately followed with exponential and logs. And that's what you're going to find here. That you're going to have exponential equations followed by logs and then properties of logs. Very similar in nature to the layout from before, but also stresses the importance of logs in the future. So there is logarithmic differentiation that you'll use in your first semester of calculus. So that first Calc 1 course, you will definitely be utilizing properties of logs, and we want you to know them. And so we make sure that that's all sound before you go in there, because they're not going to cover any of that stuff. They just know you know it by now. And so let's remind you about exponential functions. The definition of an exponential function is that it is of the form a to the x, where a is greater than 0 and a does not equal 1. And so if those conditions are met, this function will grow exponentially and is the traditional exponential function. Now, I hope that you are at a stage now where you don't just look at something and be like, okay, they're just saying that. We want to make sure that you understand those restrictions right there. Now, why does a have to be greater than 0? Let's look at some things. What if f of x was equal to 0 to the x? What would x be? What would f of 1 be? Well, f of 1 would be 0 to the 1, which would be 0. F of 2 would be 0 to the 2, which is still 0. And you get this not exponential function, but you get a flat function just like that. Right? I'll apologize. It should be at the 0 level. Let me back that out. I put it up at the 1 level. I'm not sure why I did that, but it would be, I'll put it in a different color. It would be this red line right here. Not exponential, flat. Always the same value. That's the exact same thing if we, and why they let a not equal 1. If we considered a to be 1, the same thing would happen if we considered the function 1 to the x. Then I'd have 1 to the first, 1 to the second, which is just 1 every time. Okay, and that's an issue right there. So it's not, it's just flat. Even 1 to the 0, right? Because x can be any number. 1 to the 0, it would also be 1. And so it's also flat, but flat right up here, and so not exponential. So then the question is, well, why not any negatives? What's wrong with negatives? And that's a very good question to consider. So for an illustrative purpose, I want to pick something like negative 4, if you're okay with that. They're not going to let us be negative. So let me just pick negative 4 to the x. Now remember, that's what a would be. This is allowable because the a is 4, and the negative part is just turning us upside down. Remember, the variable will always operate on what's next to it. But if you had negative 4 to the x, you think, well, there's no problem. And there isn't a problem if you just pick traditional values. Let me not call that f of x. Let me not call that y. Let me call that f of x. And so if x is 0, we get a 1. If x is, let me go 1, we get a negative 4, no problem. If x is 2, we get a positive 16. A little bit weird, but doable. But there is a weirdness there, right? Because 3 would be negative 64, and we're bouncing from negative to positive. But at nowhere is this thing 0, so something weird must be happening. There must be some weirdness going on, and that's why we don't allow it. But let me get very specific. You can put in fractional powers, and so 1/2 is legit in any one of these. So think about what that is. That's negative 4 to the 1/2 power. Hopefully that registers immediately that that's asking you to take the square root of negative 4, which does not exist. It's undefined. And therefore, that's why we're ruling out the negatives. So I think it would be a mistake for me not to talk about that. It's a very important aspect. We care a lot about domains and what we're allowed and not allowed to do. And so you really want to be a part of that. Now, this really isn't the domain. This is a function issue, a definition of a function issue, and so it's why it's defined that way. So let's make sure that you understand the graph, because some of the first questions out of the gate are dealing with the graph. So what if I ask you to graph the exponential function f of x is equal to 3 to the x? Well, what would that look like? Let's make sure we understand the parent. Well, what if x was 0? No matter what that base is, anything raised to the 0 power is 1. If x is 1, I'm already up to 3. If x is 2, I'm way up to 9, right? And getting steeper and steeper. Now, if x is negative 1, I'm at 1/3, 1/9, 1/27th, and getting smaller and smaller, going down like that. That's what the exponential function looks like, the general one. So we can tie this in, and we would hopefully that you would do that. We hope that you would do that. If you had something like f of x is equal to 3 to the, let's say, x plus 2. Well, we should know what that does. That should take our regular function and shift it 2 units to the left. So instead of going through 0, 1, we're going to shift it 2 units left and go through negative 2, 1. And then everything else is the same shape going up, coming down towards the 0 line. And it's just a straight shift to the left. That's what that thing should look like. So I'll call that problem number 2. And then problem number 3, if you had something like f of x is equal to 3 to the x minus 2, hopefully right away you'd realize, oh, that's my regular graph that was going through here, but it shifted down 2 units. And my asymptotes also shifted down 2 units. So now I'm getting closer and closer to this negative 2 line, but never touching it. And I'm going up like this and down like this, right? So you get a new horizontal asymptote there. Again, one of the reasons why they talked about asymptotes now before, so that we have a better idea of what they were, although we've seen them before, even before this class. So they'll ask some questions about the graphs. The remainder of the questions will be solving exponential equations. Now, it's not fun to you grab a calculator and solve them. They'll ask for the exact answers. And so we want to make sure that you are giving the exact answers out of that. You give me a decimal, you put a decimal into the computer, it should mark it wrong, and I'll mark it wrong. Would on a paper test as well. I don't care what a calculator output is. We want to know the number that's there. So let's take a look at some questions that I saw in the homework. As your fourth example, 4/3 x is equal to 64 over 27. So they could be as simple as that. You're just asking, what power do I put on 4/3 in order to get 64 over 27? So you just think about it. 4 to the what power is 64? Well, 4 to the third is. 3 to the third is 27. So x is obviously 3. Right? That's going to be the fastest way to do it, is to think through them. And you'll have equations like that in the homework. 5. 4 to the 4x plus 1 is equal to 64. So if we want an exact answer, then you'll be able to get a common base. Okay, and so when they ask for that exact answer, we'd like to get a common base. So if you look at 4 to a power 64, if we could take 64 and write it as a power, we should do that. So this is 4 to the 4x plus 1 is equal to 4 to the third. Now, because exponential functions are 1 to 1, if the outputs are the same, then the inputs, right, the exponents must be the same. And we can solve it like that and say, oh, 4x is equal to 2, x is equal to 1/2, and solve that exponential that way. See, a nice, easy way to go about that. Now, sometimes it's not that much of a direct connection. So, for example, if I saw 8 to the x plus 3 is equal to 32 to the x minus 7. Okay, just making something up here, but it should be something that you're familiar with. It would be sad if an Algebra 2 class did not have this for you, so I'll call this the sixth example. Now, 8 to a power is not 32. So you got to look for a different base that they have in common if we're asking for a direct answer. And you know 8 is 2 to the third, which is being raised to the x plus 3. And you know 32 is 2 to the fifth, maybe, right? If you didn't know that, you could say 2, 4, 8, 16, 32, and realize, oh, that's 5 times. Now, remember, these were being raised to a power. What happens when you take something that's being raised to a power and raised to a power? You multiply the exponents. And we get 2 to the 3x plus 9 is equal to 2 to the 5x minus 35. Perfect. So what do? We set the 3x plus 9 equal to 5x minus 35, and we're back to pre-algebra. Okay, subtract away 3x, and get 9 is equal to 2x minus 35. Add 35, and 35 plus 9 brings me into the 40s, so 44 is equal to 2x. So what's x equal to? X is equal to 22. So 22 is that magic number that would link the two together. So pretty nice. Just a reminder of some Algebra 2 principles. I saw this question in the end and thought I might get some people saying, I don't know how to do that. It's a thinking question. So it's the last example here. They said this: if 9 to the negative x is equal to 13, find 9 to the 2x. Now again, they don't want you to do any kind of magic stuff, so they're trying to avoid you being able to just drop something into a calculator. Okay, perfect. We can do this. So what's 9 to the 2x? Let's start out with what we want to find. 9 to the 2x is 9 to the x squared. Now they didn't give me 9 to the x. They gave me 9 to the negative x. So if 9 to the negative x is equal to 13, what's 9 to the x equal to? Well, 9 to the negative x is equal to 13. So that means 1 over 9 to the x is equal to 13. So there's lots of ways you could do that. So you can invert both sides, you can clear, but you'll find that 9 to the x is equal to 1/13. So this means this is 1/13 squared, which you know is 1 over 169, and you're finished. So just a nice thinking exercise of consequences of what you know as a result of being told a piece of information and then still staying within that base realm. So that's what we want out of these sections, is just good thinking and good thought process for you to follow in the future. Hopefully this helps. Let me know if there's questions or concerns.